Hi, this is Susanna Ariano, and I will be doing a strain Rosette problem for Professor Lehman and ME304. Okay, this is my red ID. Everybody's there. Okay, so we're just gonna go over the problem. It says the strain Rosette shown is used to measure strains on a structure of 6061 T6 alloy aluminum. The gauge 1 reads, so I'm just going to write it down as I go. So we are given gauge 1 reads negative 150 times 10 to the negative 6 inch by inch. This is this one. Gauge 2 reads 400 times 10 to the negative 6 inch by inch, and gauge 3 reads 250 times 10 to the negative 6 inch by inch. We need to find the principal stresses, sigma 1, sigma 2, and tau max. When you report the answers in KSI and for the stress transformation step, please explain how to use Mohr circle. Alright, so we're given this. We can also tell by the diagram that theta 1 is equal to negative 75 degrees, theta 2 is equal to 0 degrees, and theta 3 is equal to 75 degrees. We are also given the type of metal we are going to be using, so the 60, 61, T6 alloy aluminum, I spelled that wrong. Aluminum gives us a modulus of elasticity. E is equal to 10,100 KSI, gives us a modulus of rigidity, rigidity. G is equal to 3,700 KSI, and we are also given Poisson's ratio, which is equal to 0.33. Right, these are all given to us from our textbook. We don't need to solve for them. Right, and now we're going to make a plan on how to solve a strain Rosette problem. Okay, so starting off, we are given the strain Rosette data. This we already have. And then we are going to use strain Rosette equations to solve for the state of strain. Right? Then we are going to use Mohr circle to solve for the principal strains. And then we are going to use Hooke's law, generalized, to solve for principal stresses. So it's a step-by-step. So we did the first step. We have all of our givens. This is all of our data. Then we are going to use equations to solve for state of strain, Mohr circle to solve for principal stresses, and then Hooke's law to solve for the principal stresses. All right. Just make sure. All right, so I'm just going to put this off to the side. We get the equations, so we have our givens. So we're going to put, let's see, strain Rosette equations to solve for state of strain. So in this we are going to find sigma x, sigma y, and gamma xy. Right? Alright, so we have the general equation. Epsilon 1 is equal to epsilon x cosine squared of theta 1 plus epsilon y sine squared theta 2 plus gamma xy cosine theta 1, oh, that's theta 1, sine theta 1, and then similarly e2, epsilon 2 and epsilon 3 will be the same thing with different thetas. I'm just going to write them down. It's the same thing. Theta 2 sine squared theta 2 xy cosine theta 2 sine theta 2 cosine squared theta 3 epsilon y sine squared theta 3 plus gamma xy cosine sine. Alright. Okay, so we have epsilon 1 given here. This is what we need to solve for. This is unknown. Epsilon 2 is equal to epsilon x. They're equal and on the same axis. 400 times 10 to the negative 6 inch by inch. And epsilon 3 is unknown. So we have two unknowns. So we need two equations. Because we know epsilon x, we do not need the second equation. Okay, so solving for the first one, we have negative 150 times 10 to the negative 6. I'm going to leave out the inches by inches just to not have a huge mess on my paper. Equal to epsilon x, 400 times 10 to the negative 6 cosine squared of negative 75 is theta 1 plus epsilon y sine squared of 75 plus gamma xy cosine negative 75 sine negative 75. Alright, and then we simplify this. We get the math previously to save time. So I'm just going to rewrite the calculation part down. Is equal to 2.6795 times 10 to the negative 5 plus 0.933 epsilon y plus negative 0.25 gamma xy. Right, and then simplifying this a little bit further, we have negative 1.76795 times 10 to the negative 4 is equal to 0.933 epsilon y minus 0.25 gamma xy. So we're going to remember this as our first equation, right? And then for solving for 3, we're going to use this equation. So epsilon 3 is, how did I do 1? There you go. 250 times 10 to the negative 6 is equal to 400 times 10 to the negative 6 cosine squared of 75 plus epsilon y sine squared of 75 plus gamma xy cosine 75 sine 75. Simplifying this is equal to that. Cosine squared of 75 and cosine squared of negative 75 is the same thing. So there we go. Same thing with sine squared of 75 and sine squared of negative 75. 933, and same thing over here, except these will be positive. 125 gamma xy. Right, simplify this just by subtracting this value to both sides. Have 2.23 2 times 10 to the negative 4 is equal to 933 epsilon y plus 0.25 gamma xy, and this is our second equation. Right? Okay. So now we have to solve these equations. Solve for 1 and 2. Okay. So the first one we have this value, so we're here, 795 times 10 to the negative 4. 933 epsilon y minus 0.25 gamma xy. Then we have this equation, right? 2.232 times 10 to the negative 4, 0. xy. Alright, and if we look closely, we can see that these two would cancel nicely if we just subtract bottom one from the top one. So that's what we're going to do. This negative distributes to each one via parentheses. So this would cancel out. These would become negative 0.5, and then this would be negative 1.76. Wait. 795 times 10 to the negative 4 minus 2.232 times 10 to the negative 4 is equal to 0.25 times 2 gamma xy. This is negative 4 times 10 to the negative 4 is equal to 0.5 gamma xy, and this gives us gamma is equal to negative. It's both negative. So this becomes positive. Gamma xy is equal to 8 times 10 to the negative 4. So we have this one. Oh, I'm just going to box this one. And then we can use this we can solve for epsilon y by plugging this into either one of these two equations. I'm just going to do the top one. 5 times 10 to the negative 4 is equal to 0.933 epsilon y minus 0.25, 8 times 10 to the negative 4. Adding this to this side will give us 2.3, 2.5 times 10 to the negative 5, 0.933. Dividing these two by 0.933 will give us epsilon y is equal to 2.487 times 10 to the negative 5. So we got our sigma x, sigma y, and gamma xy. So we just found our state of strains. We've completed the step. Alright, going to the next part, we need to use more circles to find the principal strain. Just going to set this off over here. Okay. Right here, more circle. More circle. Ooh. To find principal strains. Principal strains. And here we're going to find epsilon 1, epsilon 2, and tau max. No, gamma max. Okay. We have this value times 10 to the negative 6 inch by inch, right? 2.487 times 10 to the negative 5 inch by inch, and gamma xy 8 times 10 to the negative 4. This is actually reading? I'm not sure. This is inch by inch so far. Alright, so then we're going to plot these. Nice big graph. This is going to be strain inches by inch, and this is going to be tau xy over 2. So this is going to be 4 times 10 to the negative 4, because we need to divide this in 2. Negative 4 times 10 to the negative 4. Right, and then we have, say the 400s around here. This is e to the x, which is equal to 400 times 10 to the negative 6. And then we have over here the epsilon y, which is 2.487 times 10 to the negative 5. Right? Okay, connect these 2 points here. Oh, that's not very centered, but it's supposed to be like centered, so that's okay. We'll just pretend it's centered. 2 circles. Oh, it's kind of an oval, but you get the point. These are the points we're trying to find. Right here. And to find that we need r, we need this distance right here. And we need this center. Okay? Right, so to find the center, we need this average, which is 400 times 10 to the negative 6, plus 2.487 times 10 to the negative 5 over 2. This will give us 2.124 times 10 to the negative 4. Right, and then we need this distance. We need d. D is equal to average minus epsilon y, which is equal to 2.124 times 10 to the negative 4. No. What did I do? Yeah. Make sure I'm right. 2.124 times 10 to the negative 4 minus 2.487 times to the negative 5. Okay. Okay, I'm right. Minus epsilon y, which is 2.487 times 10 to the negative 5. D is equal to 1.7 times 10 to the negative 4. Right? So now we can use this to find the radius. Right? This is D. 753 times 10 to the negative 4. Radius times 10 to the negative 4. Remember, this is the height. So this is this triangle. Here. And then we have r square root of d squared plus 4 times 10 to the negative 4 squared. R is equal to, just gonna plug this in. R is equal to 4.417, basically 7 times 10 to the negative 4. Alright, so now that we have our r's, we can solve for epsilon 1. Epsilon 1 is going to be the distance r plus the distance from this center. So it's going to be this distance plus this distance. So this is going to be E average plus r, which is equal to 4.4177 times 10 to the negative 4. So r plus the average, 2.12 times 10 to the negative 4. So 1 is equal to 6.54 times 10 to the negative 4. Yes, and then epsilon 2 is the same thing, minus r.
No.
What? Oh. Is it minus r? It is r minus, sorry. Is it minus r? It is this. Oh yeah. This is r. So r minus the average. It's like this. There you go. I want to say it's right. Alright. Then this is it's opposite way. Yeah, 2.12 10 to the negative 4 minus 4.1 10 to the negative 4. So then we have epsilon 2 is equal to, let's just box these, right, epsilon 2 is equal to negative 2.29 times 10 to the negative 4. Alright, and then the easiest part, tau max over 2 is equal to, this is going to be the, from the radius, so 4.177 times 10 to the negative 4 multiplied by 2, we get our tau max is equal to 8.835. There we go. These are all in KSI, by the way. These are still inch by inch, but whatever. These are still inch by inch. Alright. So now we have found our principal strains, epsilon 1, epsilon 2, and gamma max, using Morse circle. We are also supposed to tell you guys how to use Morse circle. I kind of went over it, but to find Morse circle, we have to begin using our strains. So we have our strain in the x direction, the strain in the y direction, and our gamma xy. We plotted it, we found the diameter, we used it. We used these points to find the radius and the center, which we then used to draw our overall circle, rough circle. Yeah. And that was pretty much it. Alright. So going on, so we found this part, and going on to the last step is to use Hooke's law. Okay, Hooke's generalized Hooke's law to find principal stresses. This is sigma 1 sigma 2, sigma 2, and tau max. Alright, these formulas are already given to us. This one is the modulus of elasticity over 1 minus Poisson's ratio squared times epsilon 1 plus Poisson's ratio epsilon 2, right? Sigma 2 is the same, except these two are switched, so I'm just going to rewrite that. Poisson's ratio 2 plus Poisson's ratio epsilon 1, and then tau max is equal to the modulus of rigidity times gamma max. So there you go. So solving for sigma 1, we have, it's given over here. 1,100 minus 0.33 squared. Epsilon 1 is 6.54 times 10 to the negative 4. Plus 0.33 epsilon 294 times 10 to the negative 4 sigma 1. Just use my calculator. Didn't do this one ahead of time, so give me a minute. 1 minus 0.33 squared 6.54 times 10 4 plus 0.33. Is it 294? 294 times 10 to the negative 4. And this gives us sigma 1 is equal to 6.55 KSI. Right? Sigma 2 is equal to same thing here. Minus 0.33 squared. 54 times 10 to the negative 4. 0.33 plus 20. So I just moved this over here. It's the same thing. 294 times 10 to the negative 4. Go. Sigma 2 is equal to, I'm just going to do the same. Move it over instead of rewriting everything. 0.33 plus. This gives us negative 0.15 for KSI. And then lastly, we have our tau max, which is equal to, like we said, I'm watching this rigidity 3,700 KSI times our tau max, which is 8.835. So tau max is equal to, at least I didn't do this at a time, 8.825. Oh, I think this was times 10 to the 4. 3.27 KSI. And that should be it. It's just gonna, these are our answers in KSI.